We're going to take a look at some examples of rationalizing denominators. And I'm not going to lie, I picked some tricky ones to put in this video. When it comes to fractions, we're going to always remember to reduce, and we could see that in some of these problems. We can't have a 0 on the bottom, shouldn't be an issue for us. You can't have just like a negative number sitting on the bottom, so we're going to have that probably show up and have to fix that. And the biggest thing that this whole section is about is you can't have a radical or a root on the bottom of your answer and call it done. So this video is all about really fixing this problem. Now we're going to encounter a few other issues along the way, but the new part that we're going to have to deal with is that you cannot have a radical on the bottom of a fraction. When looking at example 1, there's actually a couple different ways we could start this. As in most math problems, there's lots of ways to get to the right answer. So I'm going to show you one way, but this isn't the only way. First thing, let's point out the fact that although this is a 4 and this is a 12, and your first thought might be to reduce, this really isn't a 12. This is the square root of 12, which actually isn't 12. So we cannot reduce here. Now, if the 4 was under a radical, then yes, if they're both roots, we could reduce. Or if the 12 was out, and then we could reduce. But if one's under a root and one is not, we cannot reduce those. So what we're going to do to simplify and get rid of the root on the bottom is we're actually going to multiply by 1. Now this 1 is going to be super fancy. It's going to be a radical as a fraction. And remember, when it comes to fractions, anything over itself is 1. So as long as I do the same to the top and the bottom, we're not changing this, we're just going to make it look different, because multiplying by 1 wouldn't really change the value. Now we're going to have to be smart with this 1. Whatever we put in here, we want it to end up over here as something that we can actually do the square root of. That would get rid of the root on the bottom. So we've got to think, what is it that when I put something in here and multiply these two, I end up with a perfect square. So think back to all those perfect square numbers like 9 and 25 and 16, and I want to try and get to one of those. When it comes to the variables, in order to get something over here we're going to need x squareds. So I think that's the first hint here, is in order to get to something we can do the square root of, I need an x squared. And currently I have an x. So I need an additional x in here. Whatever you do to the bottom, you got to do to the top. So that at the end over here, we have an x squared that we can work with. Now let's talk about this number. We're at a 12. 12 times something, and then we end up as a perfect square. Now, the most obvious answer is 12. 12 times 12 is clearly something squared, so we could do the square root of it. That is not wrong, but it's going to create some more work for us at the end. There's actually a better choice here, because 12 times 3 is 36, and 36 is a perfect square. So that means over here I'm going to have 36x squared under the radical. Up top, now that 4, he's got to stay out, and the 3x is staying under. If we've done this correctly, the root on the bottom should go away. So the square root of 36 is a regular 6, and the square root of x squared is a regular x, and so we have successfully rationalized the denominator. There is no more root in the bottom of that fraction. However, there's still one more thing we can do. See this 4, he's outside of the root. This 6 is outside of the root, and 4 over 6 is something that we could reduce. So let's reduce that. I could pull a factor of 2 out of here and pull 2 out of here. So that's going to leave me with 2 root 3x over regular 3x. You may want to try and reduce here again because these 3x's are so tempting. But remember, this 3x is under a root and this one is not. And if one is under and one is out, we can't reduce. They both would have to be out or they both would have to be under. So I think we are done with number 1. Let's take a look at example 2. It's very similar, but this one is a cubic root instead of a square root. The process is the same, but we're going to be looking for perfect cubes or things on a cubic list versus a squared list. Now, before I get started, I noticed that those things are both, the top and the bottom, are both under a radical. So you can write it the way they have it written, but you could also write it like this. And maybe when you see it like that, you notice that we could reduce this. I could divide top and bottom by a common factor of 2. This is really the cubic root of 1 over 9x. So that makes the numbers a little bit nicer to deal with. I'm going to break it apart again so that we can now rationalize the denominator, because I do have a cubic root on the bottom. So we're going to have to fix that. The way we fix that, just like before, we're going to multiply by a fancy 1. Since it's cubic root, my fancy 1 needs to be cubic roots. And again, the goal is to get to something over here on the bottom that we can actually do the cubic root of. So let's talk variables. On the bottom, I have an x. So whatever I multiply with in here needs to end up over here as an x cubed because it's a cubic root. Well, if I have 1x and I need to end up with 3, that means I need 2 more of those in here. Let's talk numbers. We have a 9. So I need 9 times something and have it end on a cubic number. So remember, cubic numbers would be like 1, 8, 27, 64. And in fact, 9 times 3 is 27, which is on the list. So the cubic root on the bottom here is now 27x cubed, which is good news because we can do that. And 1 times 3x squared is just going to be 3x squared. Another way to think about that 9, if that was hard to come up with the 3, 9 is 3 times 3. And if we're doing cubic roots, we need things in groups of 3, just like we needed x to the third. So we have x and then x and x. And here we have 3, 3, and 3. We have 3 3s total to get over here to a perfect cube number. I don't know if that helps or not. But anyway, let's go ahead and simplify this guy. So nothing we can do up top. But on the bottom, the cubic root of 27 is a regular 3. And the cubic root of x cubed is x. Now remember, we cannot reduce those because the top is under a root and the bottom is not. So we are done. The way I know I'm done is there's no root on the bottom, there's no negative on the bottom, there's no 0 on the bottom, that would be a big problem, and we can't reduce. In example 3, the bottom has a lot more going on. We've got some add and subtract. When that happens, your fancy 1 has to get a little fancier. Our fancy 1 is going to need to be a little fancier. We are going to use the idea of difference of squares. So think about factoring difference of squares. One's a minus b and one's a plus b. So my bottom is root 2 minus root 10. So if I'm going to use difference of squares, the factors of difference of squares, this would be root 2 plus root 10. I make sure I change that sign so that we're using factors of difference of squares. So up top, now keep in mind we're going to have to FOIL this down here. We're going to distribute the 6 through up here. So let's go ahead and simplify the top. 6 times the square root of 2 is 6 root 2. And 6 times the square root of 10. 6 root 10. On the bottom, we're going to have to FOIL this. So the square root of 2 times the square root of 2, that's the square root of 4. Root 2 and root 10, that's going to be plus root 20. On the inside, we're going to have minus root 20. And last, it's going to be negative square root of 100. So let's see what we can do on the bottom. There's a lot of things we can do actually. Plus root 20 and minus root 20 will cancel out. The square root of 4 is 2, and the square root of 100 is 10. So what do we really have on the bottom here? We really have 2 minus 10, or negative 8. We have rationalized the denominator. There is no more root on the bottom. Now, have we created some other issues? And I think the answer is yes. First off, I notice there's a negative on the bottom. So let's fix the negative. The easiest way to do that is just multiply by negative 1 over negative 1. It's going to change everybody's signs. So this is now negative 6 root 2 minus 6 root 10 all over 8. I have gotten rid of the negative on the bottom. I don't have a 0 on the bottom. Can we reduce? The answer here is yes, we can. We could pull a GCF out from the top that would cancel something with this 8. Now, you have two choices here. You can pull the greatest common factor and reduce, or you can pull whatever is going to reduce and then reduce. So one option would be to pull the GCF, which would be 6, and then reduce the 6 with the 8. The other option, because I know 6 isn't going to fully cancel with the 8, the only thing I'm going to be canceling with 6 and 8 is a 2. So instead of pulling the whole 6 out, which you can do, I think I'm just going to pull out the 2 because I know that's what's going to cancel. So if we pull out a GCF of 2 up top, we would have a 2 sitting out here, and that would leave me with negative 3 root 2 minus 3 root 10. Still have the 8 down here. And then we could reduce. 2 goes into 2 once, and 2 goes into here 4 times. And so my final answer would be negative 3 root 2 minus 3 root 10 all over 4. If you had done the 6 instead of the 2, your GCF here would be 6. You'd reduce the 6 and the 8 by pulling out a common factor of 2. Your answer would be the same as mine, but you would probably have parentheses here and your 3 sitting out here still instead of where mine's distributed through. Both are the exact same answer, so it doesn't really matter which way you write it. You could have the GCF of 3 sitting out here, or you could have it distributed in like that. Same thing.